Hi, Sam. How are you? Janine? Hi, everybody. How are you doing? We'll start with lab 9 in a couple minutes. So if you want to check out the lab from Canvas, let me turn on the live caption here. Okay, so let's check out the lab in Canvas. Let me get my... Okay. Okay, it's 6 o'clock. We are going to get started. So today we are going to do lab 9, which is originally lab 8. We got pushed back 1 week because of the holiday before spring break. Before we start the lab, I want to point out something that I've added. So some of your classmates are concerned about the course project, and I wanted to put in a discussion thread for the class. It's not graded, but it is a good way for you to communicate with your classmates about setting up teams. So let me share screen. So if you look in the course project module, I have added the team project discussion thread. This is, I know maybe one person had posted, this is a good way for you to find your teammates. And I will send out an announcement to everybody in case students don't show up to today's session. Basically, you're just going to post a few things about what project option that you are pursuing and what makes you a good teammate and what will you be contributing to the project. So if you post that on the discussion thread, and again, you can find this in the module for the project. Let me click back here. And so if you scroll down to the course project module, that's under part 1 because you have to set up your team for the planning and the documentation and the project itself. So I put down for to-do list. This is not graded, however, but it makes sure that if you're looking for team members, you can go ahead and set up the discussion thread. And so that way you can read the post and be able to find your group. Okay. Let me know if you have any questions regarding setting up team or project requirement. I think I talked about that in the last session. And you can also go back and watch the video. So make sure we post there. So right now we are going to work on lab 9, which you will find in the unit 9 module. And don't forget that we have a quiz this week. So by the end of the week, make sure that you do the extra credit in the quiz. Extra credit's not required, of course, but it's going to help you review for the quiz. So in this week, we're going to do multiplication in LC-3, but unlike the prior lab, which is before spring break, we're going to operate multiplication faster. So the problem statement in the lab requires that we are going to do a shift add method using binary. And we are going to have input of X is at hex 3100 and Y is at 3101. Your output, your product is going to be in 3102. So on the simulator, this is where you would go and set your values, and see your product. So your program should perform multiplication using this subroutine, and that's important that we set that up. So mult1, which is an implementation of the shift add algorithm. We don't control overflow in this one. Okay. So to explain the shift add method, we would look at this part here. So given, for example, that X is going to be decimal 13, that's converted to binary 1101, and Y is decimal 43, and that is 101011 in binary. So if we manually calculate this, the way that we multiply binary is that you would have the Y, which is your multiplicand, and your X is the multiplier. So the result is going to be initialized to 0, and then we would consider the bits multiplying from right to left, just like how we would do in decimal number. We would start with the right column from the bottom multiplier, and we would go 1 digit to 1 digit and 1 digit to the next left digit. If the bit is 1, the multiplicand is added to the product. So when you multiply things by 1, it's going to be the same. So you would add that to the product line. And then when you go to the next digit, you would shift over 1 column, like what you've done with decimal number in multiplication. So for the next digit here, which is 0, we're going to shift left by 1 column. Okay. So now, because 0 multiplied to anything is going to be 0, then we don't really add that portion. Okay. It still remains the same, but we don't add. So we are going to shift and not add it. So here it says that if the bit is 0, the multiplicand is shifted to the left but not added. Because technically, if you're taking a 0, you multiply by any number, 0 or 1 in binary, it still is 0. So we are going to shift but not going to add this line. Only when it is a 1, we're going to shift for the next digit here. Okay, so as we are moving in the middle one here, we're going to shift 2 spot, and 1 multiplied by the multiplicand is the same. So we're going to add and shift. And so once you have these, you're going to add them up using binary addition. So 1 plus all the 0 is 1, 1 plus 1, we're going to do a carry 1, and so forth. So your result is going to end up like this. And so when you do this project or this lab, you need to think about how you multiply in binary. In the next section, it talks about how the representation of X, which is an input, and Y, which is another input. So when we have an X value, we really break it down to the binary digits in byte. So earlier it says that your X is 13 in decimal, so we need to break it down into 0 and 1s in binary. And the same thing with Y was 43, so we need to break it down into a group of binaries, which is going to be the 0 and 1s again. So in the representation, your multiplier is going to be the X, which is what you see in the example here. And the multiplicand is going to be Y on the top line. So when we get the product, what we would have is we would assume that both X and Y are positive. And so that means that the multiplication for that is going to be represented in a positive value. So one important thing that we want to note that in binary, multiplication by 2 is equivalent to a left shift. So when we're multiplying to the next digit, we need to left shift. Any question? Okay, so here we have the listing 6.1. And these listings are designed to help you get started on framing your program based on the requirement. So we know that we need to compute the product, which is going to be xy, y is the multiplicand, and x is the multiplier. Earlier, we saw in the explanation that your product needs to be initialized to 0. So we can either clear or initialize that in LC-3 as 0. Then we would implement a for loop. Why do we have to implement a for loop? It's because we are iterating through the binary bits. And X is a group of bits represented in binary, and so is Y. Now here we are going to exclude the sign bit. So we would say for I is 0 to 14. We're not using the 15 bits. We're going to exclude the 15 in the front. So we're only going to use up to 14. So therefore we have to iterate to 14. From 0 to 14, that gives us 15 bits. And the bit 15 in the front is going to be the 16 bit in a word. Okay. Then we need to apply the condition. If x of I is 1, then our product is going to be our product plus y, because we need to add each of the line, as you recall up here, right? If it is 1, then we add and shift. Okay, if it's 0, we just shift, we don't add. So therefore, in this line right here, it says that if x of I is 1, then we're going to take the product, we're going to plus the y, we're going to add it, and then we're going to shift left. So that means that we're going to take y plus y. Any question with this listing? Now, on this next part, it talks about how we can check from the right to left, which is your least significant bit. So if your register 1 is used as the least significant bit storage, then we need to check if R1 is 0 or 1. So that's really simple because we can branch it for 0, right? If it is 1, then we can add. So if we branch it for 0, we can send it to the other section where it doesn't add. But if it's positive, if it's not able to branch for 0, then we shift and add. So in this section, it tells you to clear R2, we initialize at 0. Then we are going to add hex 1 to register 2 because we're getting ready to implement the operation that's required here. So when we add the 1, then we are going to AND R1, R2, and put it on R0 so we can branch. So when you AND, you're going to take the register 1, which is your least significant bit, on the right-hand side, and you are going to AND it with register 2, which you have add the 1. Okay, so at this point, when you AND it, remember that the AND is whenever that you have a 0 in the mix, right? Then it's going to give you the 0 as the output. So if register 1 is a 0, then register 0 will have a 0. So it will branch to is 0. But if register 1 is a 1 and I AND it with a 1, I will get a 1. So it's going to skip the is 0 and it's going to go to the next line, which is where we're going to add. Okay, any questions? Okay, so for the next part, it talks about how we would test the next bit of register 1. That's what we talked about, right? When you AND, anytime that one of the value is a 0, it's going to store it as a 0, then we can branch. So that's how we can check to see if it's 0 or 1, so we can shift and shift add. Any question? All right, let's talk about the subroutine, aka function. So subroutine, the problem asks us to name it molt1. And we want to use this as a function to multiply. So your parameters of x and y are passed into molt1, just like how you write a function in C, C++. And we're using register 0 and register 1. The result, we're going to put that into register 2. Now, it talks about the multiplication should work even if the parameters is negative. So in the case if it is a negative number, it should work. So that means that we have to check for sign. And in the listing 5.4, like what you've seen in the prior multiplication exercise for the previous lab, we implement the sign condition. So here we would say multiply xy for the variable for the product. So we would say that the sign of the product, so we need to bring 1 to sign, because in binary representation, that bit in the front, if it is a 1, that would show that it is a negative, okay? Just like how when you did the 2's complement, you remember when we have a positive number and we convert that to a negative number using 2's complement, the front of that is all 1s, right? It's going to fill the rest of the bits as 1. So we need to represent that sign as a 1 to tell the computer that it is a negative. And with that, we would put in the condition. If x is less than 0, as it is negative, then x is negative x. So we need to convert it to a negative. And we've seen this in the last lab. So this should not be new to you. Then we would have sign is negative sign. So if y is less than 0, then y is negative y. And so we simply do a 2 complement there and a 2 complement here if it branch for negative, right? Then we initialize our product at 0. And we would say while y is not 0, we're going to take the product plus x, because multiplication is simply addition multiple times. And then we would have y is y minus 1. So if your sign, if your value is negative, then we need to make sure that we sign it, right? So our product is going to be a negative product. And so we need to implement this criteria in our program. Okay, so now let's go through and write the program, and don't forget to include your answers for this. Yeah, I have a typo here. Okay. So you can find the screenshot for this on the lab page. That will be larger than what I can show on screen through my editor. Okay. Any question before we go through the code? Okay, so in this one, we're going to put in some comments for our program information. Then we're going to start, like always, with the origination address, which is hex 3000. And like the last program or the last lab, you would start with the JSR, right? Jump to subroutine. We talked about that this week. This is the same as you would do a function call in main in a C++ program. So we would jump to the subroutine, and our subroutine is going to be called mult1, like what the problem asked. Then we're going to halt. And because our values are going to be destroyed throughout the program, we want to save and restore. Okay. So to start the function definition, you would start with save and restore. So recall that we need to represent the binaries as values. Okay. So which is why we need to make sure that our registers are going to store the 0 and 1s accordingly. So we would start with register 0. We're going to call it save reg 0, register 1, save reg 1, and so on. So here you would have a byte representation in binary. And recall that the explanation or the requirement asks us to use register 0 as the X and register 1 as the Y. Any questions regarding save and restore and why it is all the registers? Okay, so then let's think about how you write out your binary, right? If we start with 0 from the left and we go right, your least significant bit is going to be at register 7. I'm sorry, the most significant bit is going to be at register 7. So 0 is going to be the right. So here, first thing, we are going to clear out register 7. We're going to prep that and we're going to get it ready to do the sign. Okay, now we're going to start entering that part at the top here in yellow. Okay. This part for listing 5.4. So we clear out register 7. We're going to use the 1. So we add the 1 to register 7 and store it back to register 7 to make it sign. Then, because we're using the label for input X, and X, we call that it's going to be in register 0. So we're going to load the X to register 0. Then we are going to initialize it at 0. So you can do an add 0. You can use AND with 0. It's still going to give you the same result. But if you add anything with 0, right? If you start with 0, you have a 0. So here we initialize it at 0. Now we're going to check if it's a positive number. So we are going to check for it greater and equal to 0. So we are going to do a branch ZP pos. Okay, branch if it's positive number. Why do I need to do that? Coming back here, right? We need to get this ready to do this part. Okay. So now what we're going to do is we are going to test for a sign by subtracting 1. Recall that register 7 holds the 1. So after you branch for positive, now you're going to test for the sign where it would be negative. So we are going to add -1 to register 7, and we're going to sign it. So we need to do the 2 complement. So here, after I subtract 1, I'm going to do the 2's complement of register 0. Why register 0? Because that's X. Okay. Then, because if you don't subtract 1, it would be a sign value. You see, if you subtract 1, if it's 0 in the front, then it would be for positive. So you want to test to see if it's sign, so therefore we have to subtract 1. Okay, as sign is +1. So after we do the 2 complement, you would see that your register 0 would represent -X. Because we branch for positive up here, we are going to define the positive section. We're going to load Y to register 1. And we are going to initialize Y as 0. And again, we're going to branch for 0 and positive to +2. And so here we are testing to see if it is positive, just like what we did in the previous for Y. After that, we're going to subtract 1 to test the sign, just like what we did for X. And we're going to 2 complement the Y. So here you're setting up for X and Y in the case that is negative value as what is required. This part, this, and this. Okay, we nested the branches. So that was part of listing 5.4. Any question? All right, so we branch for +2, so now we are going to define +2 section. We're going to clear R2. That's where our product is going to be. We're going to clear R4, R5. So R4 is going to be added with 15. Why 15? Recall that earlier it talks about how, let me find this section, that there are 0 to 14, and then the 15 is going to be the sign bits. Okay, I just lost that section right now. Right here, I think. So that means that we have to add 15 for our loop, for the for loop. Okay, because it has to iterate through. And so R4 is going to be our loop count. Then we are going to add hex 1 to R2, because when we add the 1, that's going to allow us to add and shift. Remember that 1 is going to, because if it's a 1 value, then we can add it and shift. Then we're going to copy register 1 to register 6. Okay, so that means R6 is Y. Okay, I wanted to keep Y intact with register 1, so that's why I need to copy that to another register so I can operate different things. Now we're going to enter the for loop. Okay, so here our loop, we're going to AND Y, right, we call that R6 now is Y, and R2 is your shift bits. So 1, we're going to AND it together and we're going to put it on register 3. It's going to check the value in register 3 for the branch. If it is 0, we're going to send it to 0, right? If it is a 1, then it's going to add. Okay. So it's going to take register 0, which is your X, add it with register 5 and put it back on register 5. Now, if it is 0, then we define the section for register 0. And if the value is 0, we simply just shift, we don't add. So here you would take register 2 and recall register 2 from the previous, right? We had set it up before the loop as the hex 1 for the shift. And then in the loop, we use it to apply to the multiplier. So we are going to take register 2 plus register 2 and put it back onto register 2. So that's going to shift left bit 1. Okay. Then we're going to take X and we're going to add it with itself and put it back into register 0. So it's going to shift the value. So if you're not clear with this, this is what we're doing right now. You have to move from right to left when you're multiplying. Okay, you're going to start with the right bit, you're going to multiply. After that, you have to move left 1 bit on the multiplier, which is X. And as you do that, you have to shift the product on the bottom left as well for each of the column that you move to the left. Okay. And that's why we're doing that right here. Then we are going to subtract 1 from R4. And R4 was our count. So as we loop, we have to count down. So this is going to be for the branch. And so if it's still positive, it's still going to go. So it's going to go back to the loop and it's going to continue until 0. Then it stops. And that's for our for loop. Then we're going to add 0 to register 7. And for register 7 at the beginning, we set that up for the sign, and then we went through and as we check for positive, so that was the sign bit. So we would add 0 to that. And so if it stays 1, then it's sign, right? If it's 0, then 0 add 0 is going to be 0, so it's positive. Then we're going to branch negative and positive where it is not 0. So what am I doing here? Okay. So if you go here, this is what we're doing now. The while loop. Okay. We're checking to see if Y is not 0, and then we implement this. So at this part, we're going to see if it is, we're going to branch and it's not 0. And then we're going to do the 2's complement of 5, R5. As we define not 0, or we use not 0 up here, we have to define not 0 here. So that means that if it is not 0, we can multiply it because anything multiplied by 0 gives you 0, so there's no product. But if it's not 0, we would then store it into label P from register 5. Okay. Then after that, we are going to load, because remember earlier when you save, you store. So now you have to load register. So we're going to load all the bits back, right, to the label. And we're going to return because it is a function or a subroutine. So as you use the label, you can fill it, and we simply start with hex 0, hex 1, hex 2, hex 3, hex 4, hex 5, and so on for all 7 save register. And then we are going to fill your input, which is X and Y at the location that's required, 3100 and 3101. Then we're going to fill the product at 3102, and we end the program. So in this program, it's important that we visualize on how we would manually multiply that with the binary, and we would implement the logic in that if it is 0, we only shift and not add. If it is 1, we shift and add. And we also implement the negative value in that we would check to see if it is positive or negative. If it is negative, we sign the input, and then we also sign the product, the output. Okay. Any question?
Yeah, quick question about the code in the loop part of the program. When it branches to is 0, it's branching for whatever bit that's being added, like when it shifts over. So is that branching for like the 0 that's there, like when you shift the binary, sequence one over?
Yeah, so it's just shift and not add. So when you branch for 0, because if you're looking at the multiplier, if it is 0 right here, like this one, it's only going to shift and not add.
Oh, okay. So when it's branching for that.
Yes.
Okay.
And but you have to look through the entire group of values, right? So therefore you keep going. Okay. So for here, when it branches 0, we're going to shift left 1 bit, because if X is 0, we're just going to shift and not add. If X is 1, then we're going to shift and add. Then we're going to keep going so we're going to come back to the loop, and then it's going to check again for every single bit.
Okay.
All right. Any other question regarding the code? This one is a little harder to visualize because it's in binary, but if you think about how you multiply it and what kind of logic that you're checking for, right? And the listings in the document helps you kind of think about the applicable conditions and the loop that you would need to apply. So they already give you, some of the core components of your program, then you simply implement it. And, the earlier stuff here, we've seen it in the multiplication and division program already. So that's something that's just review for us. The harder part is to think about how you're shifting the bits from right to left and how you check that. And on the low level, the computer breaks everything down to binary. And so when you multiply, and that's physically, or we say logically, that's how it's applying the multiplication. Okay. All right. So after we've done with this, then we can go file, save as, make sure it's a .asn. Okay. And then you need to assemble it. Then in your simulator, you can load it. And as we talked about how we would use trap this week, you can take a look at the simulator before you set your values and look at the trap. So after the subroutine call, right, we had a halt right here. So you would see that it's vector 25. And then as you go down, and so when you run the program, you would also see, oh, you went too far there. Okay, so the address for your subroutine is right here. Okay, and in this one, we're not doing stack yet, so we're simply just doing, remember that this lab was originally a week before, so in this week we talk about stack, so we'll do one with stack, but the address for that is at the next line here. So and it's going to go through and store the register, and we fill that with, you know, hex 0, hex 1, and so on. So before you run your program, you need to set your values. Okay, and you can test. So we can say hex 3100, that which is your X. And so let's say if we set it to hex 3, and then 3101 is your Y, and we can set it at, let's say, hex 4. You can test it with a larger value, that's fine. Okay. Then once we set your values at the location, then we're going to run. Then you can jump to it. Oops. So 3 times 4 is 12, and that is C in hexadecimal. And you can check out the negative value to see if that works, because it should. We applied the conditions for X and Y in negative, so it should sign it accordingly. Now, when you test it with a larger value, this program has limitation. Recall that we are not controlling overflow. So when it is larger than the 1 byte, you will have overflow. So it will work well with the smaller value. And, you know, to really expand this program, we can think about how we can control overflow and simply just add another memory location to store additional bit values to represent the overflow. That's it. Just like what we've done in maybe a few labs ago, we did the overflow control. Okay. So now as you look through this lab, right, the requirements for your project is similar. You're gonna have to write at least 2 subroutines. So we need to know how to do JSR and then define your subroutine. We need to do save registers. And I normally start out with saving register. So it's kind of like setting up the variables for your functions, and you would use those variables within the function, so that way you can dynamically allocate values to it while that function is called. That, you know, so you can retain the value and not destroy it. And so I would start out with that. You can fill it with the hex value that's earlier in the memory set. Okay, so it really helps if you pseudocode things out, or even do a flow chart, and then that way you can start filling out the subtasks, because in assembly there are a lot of like little subtasks that you have to be mindful of. And if you forget that, right, you have to go back and fix it later, and that can become a little difficult, especially when you're tracking register. So when you plan out your project, you should consider laying out your program thoroughly, and then look at each section and on how you would implement your loops and your functions or your subroutines, and then, you know, load and store accordingly. Do you have any questions for me? So we do have a couple more labs. I think we're going to do a Zeller calendar program and things like that. So you would see, you know, some of the prior program being advanced. and we're going to work with an actual algorithm, mathematical algorithm, so you can see in a future lab, in the next lab. So for this one, we only implemented one subroutine, and save and restore. We implemented a loop, a while loop, a for loop and a while loop, and if conditions. Any questions? And if you missed stuff earlier, I mentioned that I put a discussion thread in the project module. It's going to help you find your team members. So if you're looking for groups to work with, post the thread, reply to the questions I posted. It is not graded, however, but I encourage you to, use the discussion thread to look for your classmates that you can work with, and then start early. I'm available for questions in case you have questions about your projects, or if you need me to look over something or ask about something, you can send email or go to office hours. Our lab is pretty fast today. Any question? Oh, we're good, huh? Okay. Well, I'm going to go ahead and stop recording because I see that you don't have any questions. I will stick around for questions in case you have individual questions or something you don't understand. And then if you are finished with the assignment or the lab, you can submit it. And then, you can put your name in the chat for attendance.